Good morning, everybody. It's a great pleasure to be talking to the Center for Power Electronics. And I think we're at a very interesting stage in the development of power electronics, because I think for the first time we can feel we have a very interesting and credible range of wide bandgap semiconductor devices. Now, we've known for some time that in principle making transistors in wide bandgap materials would give us significant advantages. Dushan has alluded to those. That the materials properties of gallium nitride and silicon carbide are very good. Hitherto, we haven't had credible devices because of the limitations of the materials, but the materials people have been working away very hard, pulled to a great extent by the LED industry, and we're now in a very happy place where we've got some devices to play with. You saw, you might have seen this, the cover of the IEEE Power Electronics magazine. We have these two figures, on the left gallium nitride and on the right silicon carbide, and they will make next generation power electronics smaller, faster, and more efficient. And following the rather nice video that Dushan played, we have blessings from President Obama. Unfortunately, we've not yet had papal blessing. We're still waiting for that one. Now, those of us who are a bit sort of long in the tooth like me will remember all sorts of semiconductor materials of the future. Where are those gallium arsenide power devices that were going to take over the world? Well, they didn't happen. So one of the questions is this real? I think the general opinion, it is real. And in any case, we ought to be trying it, even if it in the end turns out that silicon, sort of develops strongly as well. Dushan also gave us some idea of what's available. In silicon carbide, we can have the MOSFET. There's a reasonable range of MOSFETs available. The JFET sort of comes in and out, and Schottky diodes are just things you use now. And silicon carbide diodes are very good, and people are putting them in modules with regular silicon IGBTs. Over on the right is the BJT. Fairchild had a go at the BJT and then gave up, and now Genesis sells something which is clear they do not describe as a BJT, but it's current driven, so it seems to be a BJT to me. And yesterday in the various talks, I don't think I heard any mention of the BJT. Now, this may be because people have forgotten how to drive current driven devices. After all, current drive is so last century. But the BJT is actually quite interesting, and it, unlike the silicon counterpart, which doesn't share well at high currents, silicon carbide BJTs have the rather nice characteristic that they share current at higher power levels, which makes them nice to parallel. And I suppose it's my own personal interest, but I think the BJT should get more attention than it does. And also it has the advantage, and this came through on Dushan's plot, that as the temperature goes up, a unipolar device, its on-state resistance rises, whereas the BJT is quite well behaved. So I suggest that we do think a bit more about the BJT. In GaN at the bottom there, we have enhancement mode FETs, depletion mode FETs, which are usually tied in Cascode, and we'll say something more about that later, and you can get diodes too. It's actually quite hard to know what you can actually buy, what's really available. EPC in GaN, you can go to a standard catalog and you can just buy it, and they'll come. Some of the other manufacturers are harder to get devices out of. I'm impressed that Dushan, I think, managed to get something from everybody. We haven't been quite successful. Maybe our university bureaucracy is less efficient at signing the endless NDAs that were required to get evaluation devices from people like Transform and GaN Systems. But they are starting to come together. EPC really has two groups. The first group was the low voltage group. Now we have higher voltage devices. And EPC, and this will make more sense shortly, has sort of regular enhancement mode devices that are normally off, and you bias the gate positive to turn them on. But at higher voltages, many manufacturers have eschewed that option and have gone for the Cascode connection for reasons that I'll clarify shortly. Our first application area that we looked at is automotive. Automotive, like the aircraft that Dushan talked about, are a closed power system. You have a battery, which helps, an alternator, which generates the power, and various loads. And we've been looking with our partners, Jaguar Land Rover, at this problem, and indeed Dushan's student, Bo, is now looking at the problems of these closed power systems. One of the things that it seems very likely to happen is to combine the traditional 12-volt nominal bus with a 48-volt bus, because electrical loads are getting heavier and some things are easy to drive at 48 volts. On the other hand, there are going to be lots of legacy items on 12 volts for the foreseeable future. And it's quite a challenging system because if you're a Russian oligarch, you want your seat to be warm very quickly in a Moscow winter, so you've got a couple of kilowatts on seat heating. All the windows need to be defrosted, and the thing's got to start, and you mustn't flatten the battery. So it's quite an exciting system, and you don't want the system voltage to flap around too much while all that is happening. One thing is to have DC to DC converters between the 12 and 48 lines, and you can go to Messrs. Bosch and buy something. And this number here, I'm almost embarrassed to put it up. I mean, yesterday we had targets of 20 kilowatts per litre with a sort of off-the-shelf silicon converter. It's maybe 1.5 or 2 kilowatts per litre. If we were to do this with gallium arsenide, we ought to be able to reduce mass and volume and increase efficiency. So we thought we'd have a go at this. Now, I'm not suggesting that this is going to appear in 2 years' time model Range Rover, but at least with our partners, we could have a look and see what could be done in the future. Well, why would we use GaN? Obvious stuff, it switches faster, so we could reduce volume. Temperature, pretty much par with silicon. Cost, at the moment, a problem. We've got a bit of a chicken and egg on cost. If we could get the volume on wide bandgap, maybe we could get the prices down. But how do we get the volume? We have to have a low price first. I don't know whether anybody's got a good solution to that. I think the only thing is to identify applications where the wide bandgap does give real advantage and start to get the volume up. And easy to use experience. Well, not many of us have actually used GaN, and it's quite interesting when you start out. When you switch GaN, it switches beautifully. Low capacitance, really fast, great. So all those capacitances, which are smaller but are still there, currents flowing all over the place, and you've got a gate drive to look after. And when you look at the spec sheet for a GaN enhancement mode device, you think, oh, it's not quite like a MOSFET. A threshold about 1 volt. Okay, so it's quite a low threshold. We really want 5 volts to turn it on, but the gate goes bang at 6. So that's a really tight specification. With a device that's switching really quickly, there's sort of Miller currents going all over the place. It's quite tough. So this is the learning curve of our PhD student who's supported by JLR. I'm sure those of you in industry would go much faster than this, but I think it illustrates, in a way, some of the things that need to be learnt. And what happened was entirely predictable. The green trace here is the gate drive, so we turn it off. Sometime later, this is in a half bridge, the voltage at the half bridge node starts to rise. Current flows back through the drain gate capacitance at this point, and it turns the gate back on. Now you might think, actually, this is not such a bad gate drive waveform. There's a bit of ground bounce, but on the scale of things, that's not too bad. But remember, the threshold is 1 volt. Even this little bounce here turns the device back on, and you see that in the rise of drain voltage, that you get drain current through here, which stalls the rise. And that's not very good. It's losses, and so on. So some conclusions or comments. Maybe we need negative gate drive in this region. That would solve it. It's a bit of a pain, isn't it, providing a negative voltage? We don't really want to do that. That messes up reverse conduction, where we need freewheel action. And it might make difficulties in the choice of driver IC, because standard driver IC doesn't easily go negative. But you can persevere, as this student has done. Very fine product of Manchester University, who's doing a great job for us. And you could see his progress in 2 years. He's got from 100 watts to just over 400 watts. It's going to be a 4-phase converter, so in the end it'll be a 1.2 kilowatt 1.6 kilowatt converter. The efficiency's gone up, and by very tight control of layout, considerably tighter than you would with a silicon MOSFET, we've got rid of the dV by dt problems, so we're home and dry. And he's also included active temperature monitoring, and that's the device chosen. I haven't actually got a figure for the kilowatts per litre. It's certainly not 20, but it's a significant advance on the previous one. And interestingly, and what we'd expect, is that we can switch at 10 to 20 times the switching frequency of the MOSFET version. We can go to a megahertz, it just chugs away, and the losses are the same as the silicon one. So clearly, you get the benefits you might expect. However, the power density is limited by cooling. We've got bare die, GaN FETs. It's difficult to get the heat out. We went to Jaguar and said, what about liquid cooling? We could really do wonders with liquid cooling. And they gave me a filthy look and said, no, you can't have liquid cooling. We don't want to run pipes all the way around a car. So that's the end of that. So it's sometimes quite hard to sort of cash in, if you like, the benefits. But they're there. If we go to higher voltage for GaN, there are all sorts of applications that we could think about. Data centers, DC to DC. I quite like wireless charging. I have a personal belief that people would rather drive their electric car over a charging pad rather than faff around with one of those sort of horrific connectors that has got a plug for every standard that's ever been thought of that is a real fiddle to get in. Electric vehicles, we could think of drives, DC converters. As Manchester described yesterday in the converter section, drives, power factor correction. I personally quite like AC voltage regulators. That's AC to AC converters for either distribution network use or domestic use, where because it's in series with the line, efficiency is super critical, and maybe solar inverters. But of course, can these things stand the cost? This is some converters we've been building. We're not doing at the moment very sophisticated integrating converters. We're just building on regular PCBs. This is using some transform devices. This is using EPC ones, standard enhancement mode devices. And once again, we've got this old threshold voltage margin where when we turn off, when the gate voltage drops, we get this horrible return on effect here. It's harder to control this at 600 volts, as you might imagine, than at 48. And I think that's why it's fairly obvious. Most manufacturers will use the Cascode connection. A few other points. You've got sort of, well, lots of ringing, and parasitics are just so much more serious under these conditions. But they're all controllable. So the Cascode idea is that you put those of you who remember our radio frequency amplifiers, we put a MOSFET in the bottom, a regular silicon MOSFET, low voltage MOSFET. It can be very low on resistance, so the addition to the overall on-state loss is minimal, and then you put it in series with the GaN device, and that cleans everything up. And most suppliers use that configuration. You probably don't want to think too much about what happens at the drain here during switching. And it takes me back to my first experience of wide bandgap project with Denso, with my colleague Florian Adrea at Cambridge, where Denso would supply us Cascode modules, we'd test them, and without fail they would blow up, and then in the twice weekly meeting we'd have to explain to Dr. Kumar why we destroyed these extremely expensive to make modules. And the reason being is that we didn't know, they didn't know, that they were including lots and lots of extra stray inductance in that point, and so they were doomed to failure. But that's research. And if we do that, our turn-on, turn-off waveforms become really nice. These are transform devices done by my student Nikita Hari over there. So it all works pretty fine, and through her efforts, we've got from pretty slow rise times, tens of nanoseconds, down to a few nanoseconds, which means that switching frequencies of a megahertz are possible. So it can be done. Silicon carbide. Schottky diodes, as I said, you just buy them. Transistors, a bit more difficult to get, but Cree, for instance, will just sell them. And then we have a lot of new companies that we perhaps not heard of offering devices. And if you go back in history, you can think how many of the makers of thermionic valves succeeded in the semiconductor industry and how many of the companies now making semiconductors were upstarts. And we might see the same thing with wide bandgap, that we might see these new companies actually being very successful, whereas the traditional makers might not be. So there'll be an interesting fight there. Power modules, Cree. Now, perhaps missing from this list is GE. And Dushan showed some results from GE. GE is not an easy company to buy bits from, and whether they're a real supplier or not is an interesting question. What can we do with it? We saw yesterday in the converter session some very interesting results from Manchester and Imperial. Dushan alluded to the fact that we've got to sort of clean up the whole power generation act, and that biases me towards distribution network, power conversion applications rather than aerospace or automotive, but they're all there. High temperature is often talked about, and in the early days people thought that we could run silicon carbide, and you can at very high temperatures, but there are several drawbacks. One is the packaging is a nightmare. Another is that the on-state of MOSFETs goes through the roof. So I wouldn't do it unless you have to, but if you're like making special ICs for very hot places or you're building in jet engines, well, of course, you've got to do it. And HVDC is something that we're looking at, a very interesting application area. Go on. Ooh. Oh, there we go. Remember that silicon carbide is wide bandgap, and therefore you'd expect this plot. This is the breakdown voltage of a silicon carbide MOSFET and IGBT at different temperatures, and you can see at room temperature, black lines, everything is fine in terms of leakage current, but at 150, which is not a stupid junction temperature, the IGBT is leaking, the silicon carbide is fine. So it makes the point that they'll work at higher temperatures very nicely, provided the packaging will stand it. On state, the silicon carbide MOSFET red has a lower on-state voltage here at every current up to rated than a comparable IGBT. But of course I've cheated, as you always do. That's at room temperature. At a higher junction temperature, that RDS on will increase. And that's perhaps another argument why I quite like bipolar, because if we're going to run them hot, the bipolars have a lower on-state as long as we can live with the pain of base drive. We did some comparisons with those devices, and the story is totally expected that the silicon carbide MOSFET has lower turn-off energy than IGBTs by here, I suppose, about a factor of 5 or 6. Not negligible. It's not a huge difference, and I think, as Andrew Forsyth pointed out in the converter talk yesterday, yes, you can rev silicon carbide converters up to higher frequency, but not to infinite frequency. We played around, this is quite old work now, we put silicon carbide devices on a special heatsink, i.e. a heater. The reason being that in hybrid electric vehicles, you'd like to cool your power electronics with hot water, radiator water at 100-ish degrees C. Silicon carbide worked very well, and because the thermal conductivity of silicon carbide is that much higher, you can get that much more heat out, so you can cash the benefit in, not at a higher junction temperature. You can keep the junction temperature the same, but you can get the heat out much more easily, which is really nice. So you can keep the thing cool, you can have higher power density, and you can still work with heat sinks at 100 degrees. We built a half-bridge inverter and a step-up converter, a small one, it was only about 1 kilowatt. But it proved the point that with silicon carbide, compared to a cool MOS, we could get more efficiency and lower power loss. And as was pointed out yesterday, cool MOS, or super junctions, I suppose I ought to call them, are good, wonderfully low on-state resistances, but that body diode's pretty snappy, makes half bridge or bridge converter configuration's a bit tricky, and it's easier to use silicon carbide devices. These were JFETs, you could use MOSFETs, and a good switching frequency. Finally, to close the Cascode, we've been looking at putting silicon carbide in Cascode. It's routine for high voltage GaN devices. Could it do anything for silicon carbide devices? So you put a low voltage, say 50 volt MOSFET here, very low on resistance, and you put your silicon carbide device up there. That means it could be a JFET, which is a normally on device, could be a MOSFET. Bipolar won't work like this unless you do something clever. I apologize for these slightly unreadable graphs. I should know now not to make unreadable graphs. But on the left is a silicon carbide JFET. And if we look at the range of gate source voltages, it is not really what you want. Your dream is to have a VGS, which is 0 for off, and maybe 10 volts for off, on, or even 5 volts. Here it goes negative, it goes a little bit positive to get it fully turned on. So that's not nice. And it's also a normally on device. So that's a negative. If we look at the MOSFET, that seems better because all the gate voltage is positive, but they're going up to 20, 24 volts. That's not really CMOS compatible, is it? Now, we heard yesterday that there's very nice work on gate drives to make that less painful, but it's still non-standard. You had another bit of level shifting, quite a lot of you can't get a standard gate drive for it. But if we were to put these in Cascode, on the right here, you can see that it cleans up the forward characteristics. Before, we've got VGSs up to 20, 24 volts. With a Cascode, we've got VGS normal things, 10 volts fully on, because we're using a classical silicon MOSFET in the bottom leg. It also helps a bit in reverse conduction. So I think probably we should look a bit more at the Cascode for silicon carbide, because it does clear away some of these gate drive problems. And it doesn't add a lot of extra resistance. But on the other hand, like the Denso modules that we tested so many years ago, you've got to worry about what's happening at the drain of the lower device, because you've got to make sure it's under control. You do get a little bit of possibility of dV by dt control as well as a bonus. So finally, challenges. Pretty obvious, really. Circuit layout is more critical because you're using faster devices. EMC, Duchan's common mode chokes start popping up all over the place. If you have higher dV by dTs, you kick out more muck. On the other hand, if the circuit is more compact, that helps you to keep it under control. Thermal design, great, higher power density. If you take the losses up to the limit, you've got to get the heat out, but you could cash in terms of lower losses. Packaging, high temperature packaging, if you want to exploit that. Reliability, we heard yesterday about GaN FETs, those little fingers of gate sort of going funny, starting to develop defects. And availability. I think maybe we're getting a bit more relaxed about availability now. It looks as if the suppliers are going to continue. It's not like happy days when we got an email from SemiSouth saying, nice knowing you, but we're shutting down. And to conclude, yeah, they've probably emerged really, haven't they? They're here now. GaN looks pretty good at low voltage, very good at low voltage, possibly a crossover at 600. I think that's probably a sort of consensus figure. SiC, very interesting for high voltage. Can we justify the cost? And we're back to that sort of chicken and egg. How can we get volume to get the cost down? And that means we've got to look for applications where they can be used. Personally, I like applications such as the domestic ones rather than automotive or aircraft, because if you've got, say, a domestic AC to AC converter and it goes bang, it'll go into bypass mode. And then you can send a van out and you can give the house owner Marks and Spencer's voucher or flowers or something, and they're happy. Nothing is bad. But if you have a GaN converter in your Range Rover and it packs up on a cold night in a remote part of the country, you're not happy. So we need to build confidence, in my view, on, should we say, quotes, safer application areas. And that doesn't mean to say we shouldn't be looking at the challenging ones of automotive, but I think to get experience and get devices out there, personally, I'm focusing on, or putting a lot of effort into these domestic, static applications where they're more survivable. Silicon design techniques are not necessarily directly transferable, and obviously device reliability, I've sort of said that implicitly. We really want to get more stuff out there to find out how it goes, and then we can get the confidence to fly with it if we want to. And I suppose my final words are, they're great devices. Lots of us are already playing with them. We should just keep trying them in as many applications as possible and build as much experience as we can. And if they take off as they're likely to do, we'll be in a very good position to build the products of the future. Thank you.